Alternating current. Most electric devices that we use every day, with the exception of battery-operated cordless tools, use alternating current, AC. In alternating current, the flow of electrons periodically and regularly reverses its direction. This reversal of direction is caused by a changing or alternating voltage in the circuit. This causes the current to flow first clockwise, then counterclockwise. Figure 6.4 shows the electron flow in an AC circuit. Positive alternation. Negative alternation. Figure 6.4 alternating current electron flow. The device that produces the voltage causing an alternating current is the AC voltage source. An alternator, also called an AC generator, is another machine that produces AC voltage. Alternating current is more widely used because it can carry a high voltage over long distances. During any power transmission, power losses occur because the conductive material, in an electrical wire, the copper wire through which the electricity travels, heats up. Applying a very high voltage in a transmission line makes it possible to reduce the power loss in the line. A low current at a high voltage and a proportionally high current at low voltage transmit the same amount of overall power. Both voltage and current in an AC circuit exhibit a sine wave signature, as figure 6.5 shows. Each AC cycle consists of two flow alternations per cycle, a positive alternation, or the amount of time that the power output is above the axis, and a negative alternation, or the amount of time that the power output is below the axis. The negative alternation represents the flow reversal in the AC current flow. The AC output repeats these cycles as long as the conductor is receiving power. You measure the frequency of the cycles per second to assess the rate at which AC current is flowing. This frequency is measured in hertz, and indicates the number of cycles that the AC flow completes in 1 second. The electricity that you receive through the outlets in your home, provided that you live in the United States, operates at about 60 cycles. In this case, the duration of one cycle is 1/60, meaning that the AC current performs about 60 complete cycles per second, which is stated as 60 Hz. Electromotive force and voltage. Remember the analogy used previously, of current being like a river. Let's take that illustration one step further. Because you normally experience electricity through the medium of electrical wiring, let's liken it to water flowing through a pipe. Just as a pump must force water from the ground into a pipe, a source must pump electrical charge into the wire. With water, the more powerful the pump, the greater water flow you will have. In like manner, the greater voltage the power source generates, the greater the rate of electron exchange through the wire. Exam alert. Remember that voltage is the energy or pressure that makes the stream of electrons flow and is measured in volts. Current is the flow rate of the electrons and is measured in amps. In DC circuits, E for electromotive force represents voltage, while in AC circuits, V indicates the voltage. In both cases, voltage is measured in volts V and may be represented as VDC or VAC. When you are measuring voltage at a specific location in an electrical circuit, you are actually measuring the potential difference. For instance, if you are experiencing line drop, explained in the next section, this is an important calculation to determine how much voltage you are losing between 2 points in the electrical path. A voltmeter measures voltage, resistance and impedance. All materials, regardless of how electrically conductive they are, have some resistive properties, or properties that oppose the flow of electrons. In any electrical circuit, the resistance, impedance in AC circuits, of the conductive material slows the electron flow. The more resistive the conductor is, the slower the flow will be. The degree of resistance depends on the material and size of the conductor. In some cases, resistance impedance can cause a drop in voltage, line drop, and, if excessive, resistance may also cause the conductive material to overheat or burn out the load devices. Exam alert. It is important to know that line drop indicates a decrease in voltage between 2 points on a line because of line impedance, resistance. A lower current and higher voltage across the transmission line will help compensate for line drop. Materials with high resistance have low conductivity, and materials with low resistance have high conductivity. This is because high resistance materials have more free electrons than an insulator, but not as many as a conductor. As the resistance increases, the material acts more like an insulator. As the resistance decreases, the material acts more like a conductor. All materials, even good conductors such as copper and silver, have at least some resistance factor. In DC circuits, R represents resistance. In AC circuits, Z represents impedance. Although Ohm's law uses R and Z in the same capacity, impedance differs slightly from resistance, in that impedance is a calculation of both resistance and inductive reactance. You measure resistance in ohms, represented by the omega symbol, omega. The formula for finding resistance in a DC circuit is R equals E/I, and Z equals V/I in AC circuits. Exam alert. Resistance is the opposition to electron flow within the conductive material. It is measured in ohms and is represented by this formula in DC circuits, R equals E/I, where E is electromotive force. In AC circuits, we find impedance, which includes resistance, by this formula, Z equals V/I, where Vis the voltage and Zis the impedance. Exam alert. Exam alert. For the Asvab, you can solve for the DC circuit values for every question. The variances that would normally be involved for an AC circuit are not considerations in the test. Conductors and conductivity. An electrical conductor is a substance through which electrical current can flow with little resistance or, simply stated, a material in which free electrons can be easily moved from one atom to another by an outside, energizing force. One of the most conductive materials is water, because of its loosely bound electrons and fluid nature. In general, metals are very good electrical conductors, but exhibit increased resistance, meaning that the material isn't as conductive, with increasing temperature of the material. Because silver and copper can both conduct almost all the applied electricity, you will commonly find these materials as conductors. However, some composite materials also have good conductance properties. Table 6.1 describes the relative conductivity of some of the most common conductive materials.